Having studied the properties of continuous functions on closed and bounded intervals, we can move on to further properties of continuous functions defined on such intervals. So, in this section we will be learning what is called intermediate value theorem. The first theorem in this context is location of roots theorem, which states that if I is a closed bounded interval, if f is a function defined from I to R and is continuous on I, and additionally we are given a condition f of A is less than 0 less than f of B, or f of A is greater than 0 greater than f of B, then there exists a number, real number C between A and B such that f of C is equal to 0. So, why the name location of roots is because in majority of the real world situations we are using mathematics to model the situation and to find for what values and a particular equation is true. So, in such cases we will be having the equation as the function f of x and we will be searching for the root. So, if in particular we are able to find two values for which one is less than 0 and the other is greater than 0 or vice versa, definitely we can have a real number solution of that equation between the two values. So, that is the importance of this theorem, and geometrically we can look into this as we are given an interval AB where you have f of A and f of B to be one is less than 0 and the other is greater than 0. That means f of A, the image corresponding to A lies below the x axis and f of B lies above the x axis or vice versa, and also given that the function is continuous. So, whenever you draw a continuous function, continuous curve starting from f of A and reaching f of B, whatever be the shape of the graph, provided the function is continuous, definitely at some point between A and B it should pass through the x axis. So, this point is the C which is said in the theorem. So, it can be more than one point, but definitely at least one point exists because of the continuity of the function f. So, this is the geometrical aspect or geometrical view of the location of roots theorem. Now, let us see to the proof of it. So, looking at the proof of the theorem, we are given f is defined from closed interval AB to the set of all real numbers R. Also, additionally we are given a condition that f of A is less than 0 and f of B is greater than 0. So, we are restricting to this condition because the other condition automatically follows similarly. So, without loss of generality, we assume that f of A is negative and f of B is positive. So, the first interval that we are taking is exactly the same as your AB. So, A1 is equal to A and B1 is equal to B. Take the midpoint of A and B. That means, let P1 we choose as A plus B by 2. Now, you look at the image of this point f of P1. If f of P1 happens to be greater than 0, if f of P1 is greater than 0, that is the first case, take A2 to be equal to A1 same, but B2 we will take as P1. And second case is, if f of P1 is less than 0, we will shift to the next value A2 to be equal to P1 and B2 we will retain as our B itself. Now, what is the importance of doing this? Again, the same condition as were given f of A less than 0 and f of B greater than 0 holds for this interval also. That means the left side is positive, right side is negative, or left side is negative and right side is positive. Left side is negative, right side is positive, holds. So that is the condition for this. And so I2 we will take as the interval A comma or A2 B2 we can write. Whatever be the case, we can write I2 to be the interval A2 B2. So I1 is the interval A1 B1, I2 is the interval A2 B2. Now what is the length of this interval? Because P1 is taken to be A plus B by 2, the length has been reduced by half. So if altogether the length of I1 happened to be A1 B1 or AB, this is our P1. So either this is our I2 or this is our I2. So whatever happens, the length of I2 becomes length of I2 now becomes B plus or B minus A by 2, because B minus A is the total length. Now again we are going to bifurcate this interval A2 B2 using the same technology. So A2 B2 is divided into 2, so P2 becomes A2 plus B2 by 2, and if f of P2 is greater than 0, we will take the interval to be A2 P2, I3 will be equal to, or A3 will be equal to, we can write one more, A3 will be equal to A2 and B3 will be equal to P2, and if f of P2 is negative less than 0, A3 will be equal to P2 and B3 will be equal to B2. Okay. So again the length of this interval I3 becomes B minus A by 2 power 2. So in each case we are dividing the interval into half. So I3 is the half of I3 has length half of I2, I2 has length half of I1, and so on. And proceeding like this, we get a sequence In of nested intervals. Why nested? Because each interval is obtained by dividing the previous interval into half. So each interval is contained in the just preceding one. So nested intervals, and length of In becomes exactly equal to B minus A by 2 power n or 2 power n minus 1, we can write. So this is the length of each In, and we have started with In to be closed bounded intervals, and we have restricted the n points to be a point on the interval itself, and In is a sequence of nested intervals and length of In is equal to B minus A by 2 power n minus 1, and this quantity as n tends to infinity we can see that it approaches 0 because it is becoming smaller and smaller in each case. So infimum of Bn minus An is obviously equal to 0. So all these conditions could remind you of something that we have studied in the previous session, one of the previous session, which is nested interval property. And so by nested interval property, there exists a common point C belonging to In for every n. Okay. And so where this belongs to In for every n indicates that C belongs to the closed interval An Bn for every n. Or mathematically if you represent, this is something like this: An less than or equal to C less than or equal to Bn for all n, which indicates that C minus An is less than or equal to Bn minus An. Name it as equation number 1 or inequality number 1, and An minus C is less than or equal to Bn minus An, or An minus Bn, whatever it be. An minus C is less than or equal to Bn minus An. Okay. In any case, you will get Cn converges to An, and this actually does not hold. Okay. This holds. Okay. C minus An is less than or equal to Bn minus An for every n. So this indicates that as n approaches n approaches infinity, this is going to 0. We have seen, because Bn minus An is of the form b minus a by 2 power n minus 1, and so C minus An goes to 0 as n tends to infinity. So this indicates that C minus An tends to 0 as n approaches infinity, or we can say that C is approaching or Ans are approaching the point C as n tends to infinity. So this indicates that this implies limit n tends to infinity An equal to C. Now we are given in the beginning in the statement itself that f is a continuous function. So because of the sequential criteria of continuity, since f is continuous, therefore An converges to C implies f of An converges to f of C. And if you remember, we have studied a result, if we have a sequence of negative terms, it cannot converge to a positive term. And what about this f of An for every n? F of Ans are the left sides. So in every bifurcation of the interval, we had restricted our left side such that f of An is less than 0. So this sequence is actually a sequence of negative terms. So obviously your f of C should be less than 0. So therefore f of C should be less than 0 as f of An is less than 0 for every n. So similarly, a similar argument can be applied to show that Bn minus C tends to 0 as n tends to infinity. Therefore, C is the limit n tends to infinity of Bn, and again a similar argument based upon the continuity of f, we can show that f of Bn also converges to f of C. So this we can name as inequality number 2, and since f of Bn's are strictly greater than 0, a sequence of positive terms always converges to a positive term, you have f of C to be greater than 0. So f of C should be less than or equal to 0, we can write, and because f of Bn is greater than 0, f of C should be greater than or equal to 0, because it can be 0 as well, the limit can be 0 as well. For example, if we have 1 by n as the sequence, we have seen that each 1 by n is positive, but the limit is 0. So f of Bn is greater than 0 indicates that f of C should be strictly greater than or equal to 0. And f of An is less than 0 indicates that f of C should be strictly less than or equal to 0. So this can be inequality number 3. Therefore, 2 and 3 indicates that on one side you should have f of C should be less than or equal to 0, and on the other side you should have f of C to be greater than or equal to 0. So both holds means this forces our f of C to be exactly equal to 0. So we have a particular point C between your A and B where you have your function's value becoming equal to 0, which is exactly said in the location of roots theorem. So that completes the proof of the location of roots theorem. The similar argument holds for this case as well. You can start with B and f of B and f of A on the other reverse order. So using the location of roots theorem, we can solve problems like this, where we are asked to find a real number which is exactly 1 less than its cube. So, if such a question is being asked, we can think of converting this question into a mathematical expression or mathematical function and find its root using location of roots theorem. So, the question is like this: exercise 1 or example 1. Does there exist a real number which is exactly 1 less than its cube? So, let x be the real number, such that x is equal to x cube minus 1, because we are asked to find a real number whether it exists which is exactly 1 less than its cube. So, x is equal to x cube minus 1. So, rearranging this as a function, f of x becomes f of x is x cube minus x minus 1, and we can find whether this is equal to 0 for any real number x. So, look at the expression f of x and think of any suitable value which will make it a negative number. So, we can see that f of 0 definitely makes it less than 0, because f of 0 is negative 1, it is less than 0, and f of 1 also we can see 1 minus 1 which is equal to negative 1, that is also less than 0. And if we put f of 2, we can see that this is 2 cube minus 2 minus 1, which is 8 minus 2 minus 1, and that is equal to 5, which is greater than 0, and therefore you have f of 1 to be less than 0 and f of 2 to be greater than 0, which indicates that by location of roots theorem there exists a particular real number between the numbers 1 and 2 which is exactly satisfying this equation. Or by location of roots theorem we can write, by location of roots theorem there exists a particular real number c between the points 1 and 2 such that c is exactly equal to c cube minus 1. So, location of roots theorem only gives you the existence or only gives you the position where the root lies. It won't give the exact value of the root, but it gives the position or it gives the interval in which we can possibly find a solution or root. So, this was one application of a location of roots theorem. Next, we are moving on to the important result which is called Bolzano's intermediate value theorem. Again, I is given to be an interval. If f is defined from f is continuous on I and a and b are any two elements of I which satisfies the condition f of a less than k less than f of b, then there definitely exists a point c belonging to AB such that f of c is equal to k. So, location of roots theorem was saying about the position of the root. Here intermediate value theorem is a generalization of that, which says that if the function f is continuous, then it will sweep off every value between f of a and f of b, and every value between f of a and f of b definitely has a pre-image. So, definitely for any value between f of a and f of b, there exists a point c such that f of c is equal to k. So, that also can be geometrically visualized like this. Suppose this is the domain and this is some interval a b which is given say this is your f of a and somewhere here whatever be the value f of b, and you are given a continuous function which is of any shape. For any value between your f of a and f of b, you take any point arbitrarily. Here you take as k between f of a and f of b. Definitely there exists a point c between a and b such that k is exactly equal to f of c. So that is what is intermediate value theorem saying. The proof of this theorem follows from the location of roots theorem. The proof of intermediate value theorem. We can start with defining a new function, say g, such that g of x is nothing but f of x minus k. So in the statement of the intermediate value theorem, we are given the condition f of a less than k less than f of b, and if f is continuous, g is also continuous because k is a constant function, and we have seen in the session of continuous functions that if both f and g are continuous, f minus g is also continuous. So if the difference of two continuous functions is continuous, and so g of x is continuous here. So g is a continuous function, and what is g of a? G of a is nothing but g of a is equal to f of a minus k, and because k is greater than f of a minus k will be less than 0. And what about g of b? G of b is equal to f of b minus k, and because of this given condition k is less than f of b minus k will be definitely greater than 0. So we have satisfied all the conditions of location of roots theorem, namely g is continuous, g of a is less than 0 and g of b is greater than 0. So by location of roots theorem, definitely there exists some point c between a and b such that g of c equal to 0, which shows that f of c minus k is equal to 0, which indicates that f of c is equal to k, which was expected to be proved in intermediate value theorem. So that completes the intermediate value theorem as well. So this is the result. As a corollary, we have if I is a closed bounded interval and if f from I to R is continuous on I, and if k is any number such that infimum of f of I is less than or equal to k less than or equal to supremum of f of I, then there exists a point c belonging to I such that f of c is equal to k. So instead of f of a and f of b, you are specifically given the infimum and the supremum because I is given to be a closed bounded interval. So that actually follows from the maximum minimum theorem as well as the intermediate value theorem. That is why it is a corollary. The next is an important result. If I is a closed bounded interval and f is a function from I to R is continuous on I, then f of I is a closed bounded interval. So the importance of this theorem is that a continuous function takes a closed bounded interval from the domain to a closed bounded interval in the range. So that is the importance of this result, and the theorem actually follows from the maximum minimum theorem and obviously the Bolzano's intermediate value theorem. So I will give you an outline of the proof. The proof of the theorem is like this. Given f is continuous on closed bounded interval I, and which indicates that there exists small m and capital M such that f of x is greater than or equal to m and f of x is less than or equal to capital M for every x belonging to I. It follows from the maximum minimum theorem. So, this indicates that the entire f of x is contained in the closed interval small m capital M. Also, it remains to prove that, now it remains to prove that, to prove small m capital M is contained in the set f of x or the range. So, you take any value between small m and capital M, small m is exactly equal to the infimum that we have discussed in the proof of maximum minimum theorem, and capital M is exactly equal to the supremum, and so it follows from the corollary that small m capital M is contained in the interval by using Bolzano's intermediate value theorem. So, these two shows that f of x is exactly equal to the set f of x, we can say is exactly equal to the closed interval small m capital M. So, that is the proof of this result. And the last result that we have is what is called the preservation of intervals theorem, which states that if I is an interval, it need not be a closed bounded interval as in the previous case, it can be any interval, and if f is a function from a to r is continuous on this interval I, then definitely the set f of I is an interval. So, again the proof follows from the characterization of intervals theorem. Any value between the points can be swept off inside f of I because of the intermediate value theorem as well. So, the proof follows from characterization of intervals theorem as well as the Bolzano's intermediate value theorem. So, these are some of the properties of continuous functions defined on closed and bounded intervals as well as continuous functions in general, and that covers most of the theorems regarding continuous functions defined on intervals and especially on closed bounded intervals. Thank you.